Good day everyone. For today, I will be discussing about simulation of mobile robots in a virtual environment. So, in the development of algorithms to control mobile robots, it is necessary to simulate them using virtual robots in order to test their performance before implementing them to the real ones. This is done because sometimes it is too expensive or unfeasible to execute hundreds of testing operations with a real robot. So we have developed a system named a ViRBot where operational algorithms for mobile robots can be tested using virtual robots with the same conditions as if they were the real ones. So the main idea here is to be able to control the real and virtual robots indistinctly, and to test the mobile robots algorithms using first and virtual robot and the real one later. And last one is to uh, allows the testing of multiple virtual robots. So here are the tools. Using the tool is also possible. This one is the virtual. We were going to have the virtual environment first, and we will be using the WTK Sense 8, which is a powerful tool to program a 3D world applications using models. Using this tool is also possible to create boxes, tables, buildings, factories, dungeons, labyrinths, and everything needed to construct different environments where the virtual robots can be tested. Okay? There are several architectures to control mobile robots. Our architecture is based on the Aura architecture developed by Ronald Arkin. In our approach, the mobile robot's operation is formed by several layers. Each one having a specific function that is who control the behavior of the robot. We have the perception. It is one of the main objectives of the perception module is to obtain a symbolic representation of the data coming from the robot's internal and external sensors, from the human-robot interface, from the robot's task, and if chosen, from the simulator. Next one is the internals and the external sensors. In the internal sensors, each of the sensors is represented by a data structure that has the following elements: sensor's name, sensor's title, sensor's position in the robot, and a set of sensor values. In the external sensors, the robot has an array of 8 infrared sensors, 8 sonar sensors, 20 tactile sensors, and a video camera. In a simulation in the ViRBot system, it is possible to simulate each of sensor signals according to the physical model of sensors. Thus, when the system is tested using the virtual robot, the simulator provides each of the sensors' values. Next is the human-robot interfaces. The communication between the robot and the user is done by several means: speech recognition, text provided by the keyboard and control pads. In the robot task, the robot is programmed to perform certain tasks such as picking object and delivering them to another place during the day at a certain time. In a world model, the world model module uses the belief generated by the perception module, and together with the information provided by the cartographer and the knowledge representation, it generates a situation that needs to be solved. In Cartographer, for every room of the working environment, there is a representation of how each of the rooms are interconnected between them, as well as each of the known obstacles included in them. The links between the rooms are used later to form a tree that it has a root at origin room, and one of the several leaves have the destination room. Next one is the knowledge representation. An expert system is used to represent the robot's knowledge. In an expert system, the knowledge is represented by rules, and each one contains the encoded knowledge of an expert. That is, the action that can be robot would be if certain conditions were met. Next one is the goal activations. Given a recognized situation, it is a set of goals that is activated in order to solve them. Next one is the option. This is a set of hardware procedures that solve partially specific problems. Next one is the planner. Planning is defined as a procedure or guide for accomplishing an object or task. This requires searching of space of configuration to find a path that corresponds to a set of the operation that will solve the problem. Next one is the navigator. The navigator takes the overall plan and finds a set of trajectories that consist of distances and angles that the robot needs to execute in order to reach its destination. Next one is the pilot. The pilot takes the trajectories generated by the navigator and executes them. Then the control algorithms, it controls the robot motors and with incoming data from the motors and sensors. And last one, I think it is the learning. This is the system that can learn how to solve new problems using genetic algorithms, probabilistic method, hidden Markov models, and etc. Next is the sensor simulation. We have contact sensors, reflective sensors, sonar sensors, and infrared sensors. In contact sensors, in order to simulate contact sensors, we develop a simple polygon cross algorithm within a contact prism and all the world. So if the prism cross an obstacle, the sensor status change to on, indicating a collision with an obstacle. Next is the reflective sensors. These type of sensors are useful to create line-following robots. The virtual robot gets the track or floor values returned by the sensors in the robot's sensor's position. To simulate them, an average of the text cells are calculated in the position where the sensors are. Text cell is a texture element, the base unit of a texture over a 3D polygon. Sonar sensors are simulated by getting the position where the sonar beam strikes an object. And last one is the infrared sensors. As in the sonar sensor to simulate the infrared ones, it is necessary to get the position where the infrared beam strikes an object. Okay, this is the robot's movement. The simplest way to define the movement of the robot is to the sequence of straight lines. Okay, so basically to follow a straight line, the robot requires a transition from a straight line to another, and this is obtained by a coordinate transformation. Then the simulation process. The simulation process is described as follows. Creating and initializing the 3D world. The world is created adding all the objects that will exist on it, including rooms, models, lights, and textures. Then create the robot. Here, using the simple objects or 3D models, all the robots that will be used are composed, loaded, and initialized to work in the system. Then, assigning default behaviors to the robot, default values and tasks needed to make the robot's work are attached. Then, initializing communication. Here, all the communication devices are initialized. If it is required, the communication with the real robot via internet socket starts. Then wait for an order. Constantly, the data coming from the internet socket, joypad, and keyboard buffers are sensed, and the information received is analyzed. Execute an order. When a valid command is received, it is necessary activate It is necessary to activate certain tasks needed to execute the command. Then finish 3D world, kill all the processes attached to world. Then send finish, communicate signals, and close all the windows related. So the conclusion, using the virtual robot system to control virtual and real mobile robot is an easy and quick way to develop complex behaviors in the robots. The same algorithm tested on the virtual robots have been tested with slight variations in two different platforms. A custom robot with a 6811 microcontroller and the real-world interface mobile robot B14 with Linux operating system. The advantage of using simulated robots instead of the real robots is that we can test extensively robots' algorithms in the simulated ones before the final versions are executed in the real robots. So that's all. Thank you.